In this video, we will be analyzing functions of the form x to the n power, and we will use that analysis to find domain, range, intercepts, and behavior, continuity, increasing, decreasing, for a variety of functions of this type. And we'll sketch the graphs. All right, but first we need to tackle a few overarching concepts that we're going to need. And one of them has to do with the fact that how it affects the graph when this exponent is greater than 1, as opposed to how it looks when the exponent is less than 1. And that basically comes down like this. So here's a little graph. All right, here's a little graph. All right, so the main thing here is when the exponent is greater than 1, you're going to get a vertical function like this. This is what I mean by vertical. As opposed to when it's less than 1, you're going to get a horizontal function, which is going to be more like this. Okay? And so I'm hoping you can see what I mean when I say vertical versus horizontal. All right, so look, just memorize this because this is going to come into play in a variety of ways. Now, a lot of times we're going to be dealing with an n that is a fraction. So we're going to have an even number over an odd number. Okay? Or we might have an odd number over an even number. So when this happens, the thing that you need to understand is that even numbers cause limitations. So when you have an even number in the numerator, the graph has to stay above the x-axis. All right? Think about the graph of the function x squared. Okay? And x squared, this is the same as 2 over 1. So that would be even over odd. We know that the graph of x squared looks like this. Okay, that's what x squared looks like. But part of the reason that the entire graph is above the x-axis instead of looking like this function does is because when you square a negative number, it becomes positive. So anything that would have been negative becomes positive, and so you get this shape out of it. Now, on the other hand, when you have an even number in the denominator of this fraction, that causes a different type of limitation. This causes the function to stay to the right. All right, to the right of the y-axis. And the reason for that can be seen if we use the example of x to the 1/2 power. Okay, x to the 1/2 power. Because I'm hoping that you know that x to the 1/2 power is really the same thing as the square root of x. All right, so when you have a number in the denominator, that's really a root. And think about the limitations on a square root function, or any even root. You can't take the square root of a negative number. So what would have been a graph that looks like this, if this were odd, like 1/3, you can't include the negative side because you can't take the square root or any even root of a negative number. So if I keep only the right-hand side of it, it's going to look like this. Okay? Now, if I take all of those concepts that I just mentioned, the idea that when the exponent is bigger than 1, it's kind of vertical, and if it's less than 1, it's horizontal, and then if I consider the limitations of even numbers in the exponent, okay? Even numerator, it's got to stay above the x-axis. Even denominator, it's got to stay to the right of the y-axis. If you put all that together, you're going to get the following chart. Okay, so this is not something that you need to memorize. It's really just a summary of the different types of things I was talking about. I guess I didn't mention what happens if you have 1 over x to the n power. Let me just go back and do that real quick. And let's start with the example of 1 over x. Okay? Now, in my class, we've basically memorized the parent function. We know that this is going to be one of these functions that has branches, okay, like this, because of the asymptotes. There's a vertical and horizontal asymptote. Okay? So this is like having 1 over x to the 1 power. So that's an odd number, or even 1 over 1, odd over odd. So as long as everything is odd, that's not going to change this. So for example, say if this was 5 over 3. As long as all that's odd, the graph is still going to have this basic function. So the only this basic form to it. The only thing that's going to change that is if I start using those limitations that I mentioned before. Like if I have a fraction, but I have an even number in the numerator. So for example, consider this as sort of the original. Okay, as long as everything is odd, it works like this. But then imagine that instead of an odd number over an odd number, I had an even number over an odd number. Okay, now we said before that when you have an even numerator, everything has to stay above. So that would have the following effect on this graph. So watch how I draw basically the same graph. Okay, but everything has to be above. Well, this is already above, so it's going to stay like that. But this part that was below, because essentially you're raising everything to the 4th power, and that makes it positive, then it's going to be like this. Okay? Or one more limitation. What if I had the following example of 1 over x to the 3 over 4 power? All right, we said when we have the even number in the denominator, you only get to keep the right-hand side of the graph because it's like a root, an even root. And you can't take the even root of a negative number. So if I took really either one of these two graphs, but look at the original, imagine that you kept only the right-hand part of it. That's what would happen here. And so you would get a graph that looked like this. Okay, so now we really have covered everything that's on this chart. So now let's use that knowledge to do some problems. Well, look at problem number 1. Ignoring the 5 for a second, so we're picture x squared. We've known for a long time from previous classes that x squared is a parabola. So we're just doing rough sketches today. I'm not plotting points, so don't look for these to fall exactly on the right spots on the grid. But x squared has this basic shape to it. Putting a 5 in front of it is a vertical stretch by a factor of 5. Vertically stretching this does not change the domain or the range or the increasing intervals or the decreasing intervals. So for the basics, it still has the same basic shape to it. All right, so the basic shape of 5x squared is the same as x squared. So we didn't need this fancy chart, but if I wanted to blindly follow this chart in terms of odd over odd, even over odd, odd over even, then just understand that 2 is the same thing as 2 over 1. So this would be even over odd. So in terms of the chart, that puts us in the middle area. And because the number 2 or 2 over 1 is greater than 1, then that's this first version, okay, the vertical version. So of course it looks just like what I said. Anyway, so we should be able to easily describe the domain. That's just going to be negative infinity to positive infinity. The range is from bottom to top, so that's going to be from 0 to positive infinity. Notice the square bracket, because it does touch 0, 0 is included. The intercepts, meaning the x-intercept or the y-intercept, both of those are right here at 0, 0. Now the end behavior. So as x approaches negative infinity, f of x approaches positive infinity, meaning on the left it rises. And as x approaches positive infinity, f of x approaches positive infinity, meaning on the right it rises. Continuity. This graph is continuous. All right, there are no jumps or holes or asymptotes. So this is continuous. Okay, now increasing, decreasing. When I look at this graph, it is from left to right, it's going downhill from here to here, so that's decreasing. And then it's going uphill from here to here, so that's increasing. Okay, so my increasing interval is from 0 to infinity. Okay, my decreasing interval is from the left all the way up to 0. So that's negative infinity up to 0. Notice that right at 0, it's neither increasing nor decreasing. So that's why we use parentheses at 0 to show that 0 itself is not included in the increasing or decreasing interval. All right, looking at problem number 2. If I temporarily ignore the negative 1/2 in front, I'm left with x to the 7th power. Okay, so x to any odd power has the general look of this. Okay, whether it's x to the 3rd power, x to the 5th power, x to the 7th power, this is the general shape of that type of graph. Okay, it's bigger than 1, so it's going to be vertical and not horizontal. And again, in terms of my little magic chart here that has all these wonderful details, if I really wanted to blindly follow the chart, I could look at this as 7 over 1. All right, that's odd over odd. Okay, so that puts me in this part of the chart. So it's going to be one of these, and it's bigger than 1, so the graph looks like this. Okay, now, before I get too carried away, now I need to uncover this and see how that changes the graph. So because of the negative, that's a reflection over the x-axis. So this entire thing really has to be upside down. Okay, so in that case, it's going to be going like this. Okay, and just remember, when the leading coefficient is negative, the right-hand side is going to be down. The 1/2 aspect of it, that's a vertical compression by a factor of 1/2. That's not going to affect the general shape of the graph. So that doesn't change what I'm going to draw. So the domain is negative infinity to positive infinity. Okay, the range is also negative infinity to positive infinity. The intercepts, the x and y intercept are both 0, 0. And behavior, as x approaches negative infinity, f of x approaches positive infinity. And as x approaches positive infinity, f of x approaches negative infinity. That means on the left, it rises. That's the first line. On the right, it falls. That's the second line. This function is continuous. There are no jumps or holes or asymptotes, so this is continuous. Okay, increasing, decreasing. Well, from left to right, this is falling the entire way. This graph is decreasing everywhere. So increasing intervals, there are none. Decreasing intervals is, well, that's the entire domain. So it's decreasing from negative infinity to positive infinity. The whole thing is decreasing. All right, problem number 3. If I ignore the 2 for a moment, then I have x to the negative fourth power. And that would be the same thing as 1 over x to the fourth power. Okay? Now remember what we talked about. If everything is odd, or if I just had an odd number, then I have this. Okay? I just have these two branches. But as soon as I have an even number involved, then I have limitations. Now, if I just have the number 4, okay, that's like 4 over 1. So that 4 is in the numerator. So an even number in the numerator is the limitation that makes everything stay above the x-axis, okay, because it makes everything positive. So that's what we're dealing with now, is a picture like this. Okay, so does the 2 change anything? No. Having a 2 there, that's just a vertical stretch by a factor of 2. That just makes the graph taller, but I'm not being that precise anyway. So the general sketch, the general form of the graph is still like this, regardless of the 2. Okay, so this is the image that I will use for the domain and range and so forth. So the domain, because of the vertical asymptote, I'm going to have to split the domain into 2 parts. So the domain is going to be from negative infinity to 0, union 0 to infinity. Okay, the domain does not include 0, so I have to leave 0 out very carefully. For the range, the y values of this graph are 0 to infinity. All right, and 0 is the asymptote, so I use parentheses, 0 to infinity. Intercepts. This graph does not touch the x-axis or the y-intercept, or the y-axis, so there are no intercepts. End behavior. As x approaches negative infinity, meaning as we go to the left, f of x approaches 0. To the left, the graph is getting closer and closer to 0. And as x approaches positive infinity, meaning as we go to the right, f of x approaches 0. On the right-hand side, it's also approaching this asymptote. It's approaching 0. So this does have an asymptote, so it's not continuous. An asymptote is called an infinite discontinuity. So I will say infinite discontinuity at x equals 0. Infinite discontinuity at x equals 0. Let's do increasing and decreasing. From left to right, this portion of the graph is increasing. See how it went uphill when I drew it? And this portion of the graph is decreasing. See how it goes downhill as I draw it. Okay, so increasing intervals, that's from the left to 0. When I do these intervals, I'm staring at the x-axis. So I'm not going to say from negative infinity to positive infinity, all right? As far as the x-axis goes, it's from the left to 0. Okay, so that's why I say negative infinity to 0. The decreasing intervals, okay, this part is decreasing, but staring at the x-axis, this part goes from 0 to infinity. So it's decreasing from 0 to infinity. Looking at problem number 4, if I ignore the negative 3 for a minute, then this is the same thing as having 1 over x to the 7th power. Okay, so this is simply odd. So that would have the shape like this. Okay, when everything is odd and you have 1 over x to an odd number, that's when the graph looks like this. You have these 2 branches. Okay, however, all right, the 3 is not really going to change this because that's just a vertical stretch. But the negative is a reflection over the x-axis. So this needs to be turned upside down. So that's why the branches instead will be here and here. Okay, but nothing will be missing. There are no even numbers here, so it doesn't have to stay above and it doesn't have to stay to the right. Okay, so looking at this picture, the domain, we've got this vertical asymptote here, so I've got to be careful. So it's going to be negative infinity to 0, union 0 to positive infinity, or I've got to leave out the y-axis. And the range is going to be really the same thing, even though I'm looking up and down. It goes from negative infinity to 0. I have to leave out 0. So negative infinity to 0, union 0 to infinity, okay, here to here. Intercepts, there are none, doesn't touch the x-axis or the y-axis. End behavior. As x approaches negative infinity, in other words, as we go to the left, f of x approaches 0. On the left side, it's approaching this asymptote. And as x approaches positive infinity, f of x approaches 0. On the right-hand side, it's also approaching 0. So there is an asymptote here, so that is an infinite discontinuity. So I'm going to say infinite discontinuity at x equals 0. Increasing, decreasing. From left to right, this part of the graph is increasing. See how it's going uphill? But guess what? This part of the graph is also increasing, also going uphill. So I do have to write that separately because 0 is not included in the domain at all. So, well, really, the entire domain is increasing. So I'm just going to copy the domain. So it will be negative infinity to 0, union 0 to infinity. It's decreasing nowhere, so I'll just put none. Okay, so number 5, again, ignoring the 3/4, I have x to the negative 3 power, which is the same thing as 1 over x to the 3rd power. Okay, so that's just going to be the usual branches, all right, just like 1 over x, all right, when it's odd, changing the exponent doesn't really change the shape of the graph. So I have this. Now, having it be a 3/4, well, that's just a vertical compression by a factor of 3/4. So, you know, that's really not going to change anything. Okay. That's not going to change the shape of the graph. So the domain and range and such, it's going to be almost the same as the previous problem until we get to the increasing, decreasing part. Okay, so I just literally copied all this stuff from the previous problem because all that stuff is going to be the same thing for the same reasons. The only thing that's going to change is the fact that for this function, from left to right, this is decreasing and this is also decreasing. See how it's all going downhill. So the entire domain is now decreasing. So when I talk about increasing, I'm just going to say none. There are no increasing intervals. And when I talk about decreasing, I'm going to say negative infinity to 0, union 0 to infinity. The whole domain is decreasing. Okay, and then there's number 6. So if I ignore the 7 in front, this would be the same thing as 1 over x squared. 1 over x squared. So now I've got an even power. Okay, so the original function, like if this were odd, I would have like a branch here, and I'd have a branch here as well. But because this is even, this is going to be a limitation. Either it's going to stay above the x-axis, or I will only keep the part to the right of the y-axis. Which is it? Well, this 2 is like having 2 over 1. So this 2 is in the numerator of the exponent. Okay, and what we said was when we have an even number in the numerator of the power, that's when we have to stay above the x-axis. So my example was like this middle one. All right, 4 over 3, it looked like this. And having 2 over 1 is the same thing. Okay, or in terms of my little chart, this is even over odd. Okay, so that puts me even over odd, that puts me in this column because it's 1 over x to the n power. It puts me down here. So the picture, either way, the picture looks like this. Okay, so I need to modify this because of the limitation of even numbers. Okay, even numbers in the exponent. So the graph is going to look like this. So the domain is going to be negative infinity to 0, union 0 to infinity. The range is going to be from 0 to infinity. There are no x-intercepts or y-intercepts. On the left it approaches 0, on the right it approaches 0. So as x approaches negative infinity, f of x approaches 0. As x approaches positive infinity, f of x approaches 0. There is a break in the graph. There's an asymptote. An asymptote is an infinite discontinuity. So I will say infinite discontinuity at x equals 0. Increasing, decreasing. From left to right, this part of the graph is increasing, and then this part of the graph is decreasing. Okay, so increasing interval, that's from negative infinity to 0. Stick to the x-axis when you do this. So it's decreasing from, it's increasing from here to here, negative infinity to 0. And it's decreasing, if you look at the x-axis only, it's decreasing from here to here, 0 to infinity. Remember, for increasing and decreasing, you only use parentheses, no brackets. Alright guys, that's going to do it for this video. Go ahead and click here in the red apple to watch the next video. Click in the green apple to subscribe, or click the yellow apple for the full playlist.